Okay, so this paper is titled Statistical Inference of Motion in the Invisible. And the problem is that, let's say we are given a multiple camera setup. The different cameras, the 4 different cameras are shown in different colors here. And we say that there is an invisible region which is not covered by any of the cameras. So the question is it possible to infer anything about this invisible region, whether it be the motion of objects or some salient properties of the region itself? And we assume that the correspondences are available, which are shown with the colored marks over here. And this is only possible if we assume that the motion of objects is not independent. That is, the motion of one object is constrained by its neighbors, both spatial and temporal. So here's the overview of the solution. We are given as input the correspondences across the invisible region. And what we do is we first infer the motion of objects inside the invisible region by coming up with trajectories. And once we do that, we find some salient properties of the region, such as the typical patterns of motion inside the region, which are shown with this mixture of Gaussian here. The color shows the direction. And what are the typical stopping locations in the region, shown with the stop signs. And also, at what times did the object stop. So this is the input, position, velocity at time, at entry, at exit. Okay. So the first thing we do is we reconstruct the paths, and by connecting the entry and exit locations such that there are no sharp turns or bends. And this is only spatial, it doesn't contain any notion of time. So first we introduce 4 constraints. The first one is collision avoidance, which says that the 2 vehicles shouldn't occupy the same point in space-time. So in this figure on the left, there are 2 vehicles, green and black, and they occupy the same point, and the collision point is shown with the red sphere. On the right, the trajectories are modified and after the inference, and they don't collide. So mathematically it's stated like this, which says that the cost is proportional to the product of velocities and inversely proportional to the distance between the point of closest approach. The second constraint is vehicle following, which for this we define leader-follower pairs that are adjacent vehicles that have the same entry and exit pairship. And what this constraint says is that the trajectories of leader and follower should be time-shifted version of each other. Mathematically it is defined like this. What it does, it penalizes whenever the follower gets ahead of the leader, and it maintains that relationship throughout the travel. This third constraint is the smoothness, which is given by this. What it says is that there should not be any abrupt acceleration or deceleration. The amber trajectory is the smooth one, the black one has abrupt acceleration. And finally, the stopping behavior localization, it says that it localizes where the objects should perform the stopping behavior. Essentially, it should be close to the points where the paths intersect. So if we place exit time as entrance time points on the path, we get a constant velocity parameterization, and this reduces the 2-dimensional case to 1 dimension. Now we only need to find the times at which the vehicle was at each point along the path. But still, this is under constraint problem. There are thousands of vehicles invisible for hundreds of time seconds. So what we parameterize the trajectories using the 3 variables: deceleration, wait time, and acceleration. And since the endpoints and velocities are assumed to be known, we just need the 2 variables, deceleration and wait time, and we parameterize all the trajectories using these 2 variables. So for the minimization, since we need to perform inference on all the vehicles, we need some sort of prioritizing function, and this is based on the exit and entrance times. And we use earliest exit first, which is given by this, and we minimize the sum of all costs over the 2 parameters we start with the uniform grid search within these bounds, and then we fine-tune with the interior point method where the sum of costs is the function, and this provides 4 set of constraints. We conducted the experiments on these 2 data sets, Lancashire and Peachtree. That Lancashire had 1,211 vehicles, Peachtree had 657 vehicles. These are the inferred trajectories. And qualitatively, here we have two vehicles, each row is a vehicle. The yellow is the constant velocity, green is the ground truth, and red is the proposed method. Other vehicles are shown with black circles. And as you can see, as we progress along the time, the constant velocity collides with several vehicles here and here, while the proposed method and ground truth wait for the other vehicles to clear up and then move. Similarly, on this here, the yellow collides with several vehicles, whereas the proposed method and ground truth wait till the area clears up. Similarly, these again are in space-time. If you just use constant velocity, we have lots of collisions and they're all straight. And with proposed method, you can see there are no collisions, and the vehicle following behavior is also visible as they have the same trajectories. And similarly, the quantitative results, these are per trajectory comparison, and this is for over the whole data set. The green is for Peachtree, and the red is for Lancashire, and the dotted lines are constant velocity, the solid lines are with the proposed method. So as you can see, it's a 20% improvement in both the cases. For statistical representation, these are the motion patterns shown with the orientation shown with the color wheel. And as you can see, the constant velocity, you have mixture of Gaussians which are very similar. They have the constant velocity, whereas the proposed method and ground truth show the acceleration and stopping behavior in both of these cases. We can infer some statistics, some structure about the scene. These are the locations where the vehicles typically stop, and we get this by performing KD over where the vehicle stop. As you can see, this is the intersection, and here the vehicles queue up before the intersection, and these are the correct locations. And we also find the typical times at which the vehicle stopped, and this corresponds to the probability of green light. The blue is the proposed method and black is the ground truth, and these are the results for two data sets. As you can see, they are aligned and are correct.